Are you making an announcement?
No, I was thinking this might be easier for you to hold up.
Oh, great. Thank you.
The only thing I'm afraid of is feedback. So if you're using this, maybe switch the recording off.
Okay. Okay. All right. So we spent some time talking about the temperature anisotropies in the microwave background. And yesterday, I saw, in the accelerating into the future, I think this was yesterday. Yes, it was yesterday. A whole bunch of history, right, of the development of accelerators. And that kind of inspired me. Well, let me show you the history since we put it into us, this I think, fairly nice video done by an undergraduate who was working with me a couple years ago named Forrest Funkhauser. And to me, this is really an extraordinary thing that Sanyeev and Zeldovich, a few years after the CMB was detected, they actually predicted these acoustic peaks in the CMB. And we get to see that unfold here 50 years in 4 minutes. Would it help to turn the lights off? Is any music coming out in the room? So that's the power spectrum on the x-axis. With this will get rescaled as the measurements get better. These, of course, are just upper limits. By the way, the first thing here is 1967. That was 1 year before ultimate frisbee was invented. Since there was a question, I looked it up. That's what I'm here to do. All this time, there were theoretical predictions that were like a factor of 10 below where the upper limits were. And the theorists kept going back to the drawing board and coming out with lower predictions. Getting close. This is when I start graduate school. Second year graduate school, first detection. I worked on that experiment. Okay. Thank you. So, thanks to Forrest Fonkhauser, undergraduate student who really was the perfect combination to do this, somebody with an aesthetic sense and great technical skills too. So thanks for watching that with me. Let's see, I think I'm done for now with that, although I'll come back to using the projector. And
Car door while submerged underwater. A fatal.
what's the problem with using YouTube? Okay. Hopefully this, won't feel like you're submerged underwater, figuring out how to open the car door. Right. There was one other thing I wanted to show you. Not this. There was a, this. So we just saw this, and this temperature power spectrum, these measurements. And then there's also this E-mode polarization power spectrum. And that's what we're going to be talking about today by request, CMB polarization. And then also by request, we'll talk about the DAISY BAO results. OK, I guess I can leave this here. So CMB polarization. So I want to talk about first about how you generate polarization from unpolarized light. And it turns out what you need from the unpolarized light is a quadrupole moment incident on an electron. And let me explain why. So let's say we have a free electron here, and we have some, let me put this at the origin of our coordinate system, axis, the y-axis, and the z-axis. And now we imagine that we have some light propagating towards the electron from this direction, and it's got an equal amount, equal amplitude, polarized this way, and equal amount polarized this way coming in. So it's unpolarized. And then I'm going to draw this bigger. And then over here, we also have light coming in towards the electron, and its two polarization states are also equal, but this light is less intense than here. And this does have a quadrupole moment, right? This is the 90 degrees over here, and we have a variation in the intensity of the light over 90 degrees. And what happens as we scatter off this electron? Well, you can think about the electric field wiggling this way makes the charge wiggle back and forth. That doesn't lead to any radiation, wait, that does lead, let me back up to just looking at which polarization states can actually propagate here, right? So if we're going to be, we're just thinking about what scatters in the z direction, right? So there'll be light going in all kinds of different directions. But in the z direction, the only polarization, this polarization state, which is in the z direction, right, isn't going to survive. That's not going to propagate into the z direction, whereas this one will. And so what's coming out here from this light is just this polarization state. Right, that propagates. And then from over here, we've got, this is in the x direction here, and this is in the z direction. This one, right, is in the z direction. So coming over here from the y, what survives is the x direction. So the net result coming out in the z direction is we have polarized light, right? So we have incident unpolarized light, but with this varying intensity. And the key thing to have is a quadrupole moment, and this intensity pattern does have a quadrupole moment. We get out linear polarization, right? So there's a greater amplitude in this polarization state than in this one. So that's how you can generate it. More mathematically, if you looked at the scattering amplitude for this process, there'd be a dot product between the polarization states coming in and going out. And that dot product basically generates a cosine. And then you square that amplitude to get a cross-section. And so you've got something like cosine squared theta. Well, that's y2m. You make that out of y2, out of y2m. So you're integrating your incident light over y2m. You need a quadrupole moment to have that be non-zero. Okay, so that's how you generate it. You need free electrons, and you need a quadrupole moment. So how do you measure it? Thinking about measuring is helpful. Well, at least it's helpful to me in understanding what's going on here. So let's define a coordinate system. And if we have some metal here that can that has charges in it that can move around in response to the electric field. Now let's say we have electric field come in here wiggling like this, and it's going to move charges around in this metal, which will dissipate it. And if there's a method for detecting that heat that gets dumped into this, we can measure the intensity of light that wiggles in this direction. Light that's wiggling in this direction can't do that and passes right through this detector. So this is a polarization selective detector, and let's say that we're using it to measure. Let's call that intensity that we measure with this IY, right? So it's the electric field oriented in this direction that it's picking up. We'd also want a detector organized like this, where the signal there would be picking up is IX, and the Stokes parameter, this one Stokes parameter describing linear polarization, we label with Q, is, with what I've set up here, is IX minus IY. There may be a divide by 2. Look up an actual resource rather than my notes if you're doing anything where factors of 2 matter. And, but this doesn't tell us everything about the polarization field. Let's say we had light polarized in this direction. That would produce as much signal in this as it would in this. So light polarized in this direction, we'd get Q equals 0. So we need something else to measure, to fully measure things. And it's useful to define a rotated coordinate system. And we could lay out detectors like this and like this. And call this IY prime and this IX prime. And the Stokes parameter U is then IX prime minus IY prime. So these two numbers, Q and U, are what we need to describe linear polarization. That's the polarization. We don't get there's also a Stokes parameter V, which is you only get with circular polarization. We're not generating that here in this this setup. We need some birefringent material, say, that delayed one of the polarization states, in which one of the polarization states propagated faster relative to the other. Then we could turn linear polarization into circular polarization. But we're just talking about linear polarization here, which is all we're getting in the standard cosmology, and all we'll be talking about today. So Q and U, how can we think about these? So if we're polarized in this direction, this is all Q, and this is going to be positive. There's no U to this, right? And if we look at IX prime and IY prime, they're going to be the same. They're going to be picked up the same intensity from something like this. So that's U equals 0. This is, oh, sorry, did I get the sign right on that? Yes, I did. And then this is also Q, but with the opposite sign. Right, this is, because now this detector is being, yeah, it's IX minus IY. So yes, so this one comes out negative. Again, we still have U as 0. And then this is Q 0, and U is negative. And this is Q, again, 0, and U positive. OK, so that's, yes?
So let's see, the intensity being the, so if the intensity is just the sort of power per area, then wouldn't it be equal to U because it's the length of a 2D vector that's just been rotated by 45 degrees?
So if we have, the question was, if it just power dumped in, wouldn't Q be equal to U? But let's say we have light that is, just, it's completely polarized. It's just oscillating in this direction. It's going to have IX non-zero, but IY is going to be 0.
I see. I saw it. There's a minus sign in there.
OK. Oh, yeah. So right. So I mentioned V. I mentioned QU and V. The third, so I should bring in the fourth Stokes parameter of the intensity, which is the sum, right? Yeah. OK. OK, so anyway, this is how we describe the linear polarization. And you've seen how it's generated. So let's look at it in the context of the CMB. So at Z much greater than 10,000, the mean free path for photon scattering is, yes?
Yeah, we are talking about the E modes, right? Not the B modes.
So far, that's going to come up for sure.
But you said that we just have this linear polarization in the LambdaCDM.
Yeah, and linear B modes are still linear polarization.
All right.
So we'll get to E modes and B modes and what those are. Yeah, pretty soon actually. Together with a story about how when I was a grad student, I set back the theoretical discovery of B modes by 2 years. So yeah, that's my favorite part of this whole lecture is about the B modes. OK. So at Z much greater than 1,000, there are no quadrupole moments. There's lots of free electrons around to scatter off of, but there's no quadrupole moments. The reason is that if you think about what a free electron sees, the mean free path is really short. So any free electron is just seeing light that's coming from right next to it. And so all it is seeing is a dipole moment, right? That the mean temperature and a dipole moment that could be associated with its peculiar velocity with respect to the plasma. That's it. There are no higher order moments. Scattering isotropizes light, right? And if the mean free path is 0, you're maximally scattering, right? You notice that on a foggy day. On a foggy day, you've got light coming to you from everywhere. It's much less anisotropic than on a sunny day where it's all coming from the sun. Yeah.
If scattering anisotropic, wouldn't it just get rid of all the polarization?
Right. It's also getting rid of all the polarization. So there's no polarization, and there's no intensity quadrupole moments. There's two things we need to create polarization. We need quadrupole moments in the intensity, and we need free electrons. We have the free electrons in spades, but we have no quadrupole moments at Z much greater than 1,000. OK, and then let's go to 10 is less than Z is less than about 800. Here we have quadrupole moments because at any point, this is after recombination. So the free streaming lengths are large. They're like the size of the universe at the time, the Hubble radius at the time. And so you're definitely generating quadrupole moments. You've got you're seeing this last scattering light from this last scattering surface around you, and there's temperature variations on it, and free streaming is definitely resulting in quadrupole moments. But there's no free electrons. So again, we don't get polarization from this epoch. So where we do get it from is z less than 10, where the intergalactic medium has been reionized. And there's about 5% of the photons we see today last scattered here. Right, that's that tau equals 0.05. And then we also get it from, right, while the universe is recombining, so 95% of the photons come from this. And this is all generated at z less than 10, this little bump out here. And this is, in fact, this is the amplitude of this bump is how we measure the optical depth of Thomson scattering. And this is all from this recombination epoch, where we have some free streaming happening. The mean free path's starting to get large. So we have some free streaming happening, which is creating quadrupole moments. This is an and sign. And we also have free electrons to do the scattering. So let's look a little closer to what's happening. And let's look at the pattern that gets created. And now we're getting closer to this distinction between E and B modes. I'm going to draw here just the crests and troughs of a plane wave in temperature variation in the plasma. So this is hot, cold, hot, cold. And let's say we have a free electron here. And let's say that the mean free path is about lambda over 2. Right? So this is the co-moving mean free path, which is and then since it's co-moving, there's a 1 over A. So this electron is going to be seeing light coming to it from this direction and from this direction, as well as from here and from down here. And now think about what kind of light is going to scatter towards you, especially if you're right in that direction. So the light coming from here is brighter, and the light coming from here is dimmer. We have a quadrupole moment. And what way is it going to be? The light coming out of the board, what way is it going to be polarized? Thank you. Yes. So the light coming out of the board is going to be polarized in this direction, because you've got you get both polarization states coming out, but this one's going to be bigger than the one that, it's not completely polarized in that direction, but there's less light in the opposite polarization. So yeah, so let's just draw it like this. For our net linear polarization is in this direction. And then if we looked at an electron here, and it has light coming in from here and here and here and here, then we're going to get the opposite sign. Right? We just flipped this. Dimmer light coming in, and brighter light coming in this direction. So that's the opposite sign. We're going to get this. And if we have an electron here, we'll have this, et cetera. So this is the pattern we get. let me right now I've just drawn it out. You know, this is one peak. This is another peak. Right? This is the bottom of the trough, if you like, because this is negative. Let me add a little more to the pattern. So it's decreasing in amplitude, changing sign, and then it'll oscillate back. That's the kind of pattern we'll get, right? Where this is the variation, that's the direction of variation of this Fourier mode. And this pattern is what we call today an E mode. And from density perturbations to in linear perturbation theory, this is all we get out. All we have, everything looks like this. We've got a whole bunch of Fourier modes. However they're aligned, they set up the direction of, they tell us the direction of variation. That's the direction in which the polarization amplitude varies. You always get this kind of pattern. Now, you add a bunch of them together, you got some going this way, some the k direction is this way. You add all those up, but that's still just a sum of E modes. One thing that and this has positive parity. So under inversion, the sign doesn't change. But there's another pattern that we can get. So that's all we get from scalar perturbations in linear perturbation theory. But let me tell you about gravitational waves and how they create quadrupole moments. So here I'm just setting up a coordinate system. And let's say we have a gravitational wave propagating straight out of the board. And at the moment we look at what it's doing in the board, it's stretching out space in this direction and compressing space in this direction. So gravitational waves have polarization states as well, right? And so I've just drawn a particular polarization state for this gravitational wave, right? We could be rotated in any way, but anyway, I chose to draw it like this. And let's say that we have, let's say someone out there is basically is looking at this gravitational wave coming straight at them, and they're looking at the light that's propagating to them from here, and they're right on the z-axis. They're right on the z-axis. This light is coming out of the board and angled just to hit the z-axis just as it gets to the observer out there. So this is light coming in slightly off axis. And there's also another point here where we're looking at light coming from here. And as this light's traveling to us, the expansion of the universe is redshifting it. The wavelength's getting stretched out. But there's also this compression happening, which has some projection onto its line of sight, because it's not. If we're coming right down the axis, then it would have then this stretching and compressing would have no impact on it. But there's some projection of this onto its direction of travel, and this compression that's happening. Just think of this as a wave that's such long wavelength that it's at nearly DC limit, right? So you have to, in principle, this is oscillating, and you have to integrate up this effect. But because of this compressing of space, it redshifts less on its way to us. And this one has the opposite thing happen. And if you had to describe, if you thought about the light that observer back there is seeing as a result of this, what kind of distribution of light would you say this is?
Why
Okay.
wouldn't the stretching just influence the different polarizations of the two differently?
This is actually, means that over time there is less space to be traveled here as this thing is going. It's going in this direction too, but it's also working its way towards the origin. And it's that change in the distance. It's becoming a shorter distance.
Why does this change the intensity?
It's changing the wavelength. Could you think about? Okay, and it's changing the. It's changing the intensity because it's also. This process. One way of thinking about it is this process preserves the black body distribution, and if you're looking at a different, if it's the wavelength is less stretched, it'll be brighter. Another way but that might not be satisfying. Another way of thinking about this, that was just in my head, is that there's also a time delay. There's also less of a time delay effect. I mean, think of this as less expansion has happened. There's anisotropic expansion happening now. Along the path that this photon took, there's less of it. And so there's also.
But the expansion from that one photon, it's happening differently in different directions. It's like it's being.
Yeah.
Like it's like stretched in one direction but squeezed in the other. Wouldn't that just change the relative?
Along the path this is taking in, this is coming in from here, right, and getting to here. So what it's experiencing is this compressing of space.
Didn't we say it's going out of the board?
Yes, it is, and nothing's happening in this direction as far as stretching or compressing of space is concerned. So I'm focusing on this part of its travel.
Is its momentum directed a little bit towards the origin, or is it just moving?
Yes. So sorry, I know it's a lot to absorb. There's an observer out there, who's on the z-axis. This light here is traveling to meet that observer on the z-axis. That there's a component of motion in this direction is really important to there being any effect at all. Yeah.
What kind of angular scale is this observed on, I guess?
So this is at this point this could be anything in my presentation on any angular scale. In practice, where you get the biggest signal is on degree scales, and I can come back and degree angular scales, and that's because, well, anyway, let me get the more of the story in place. We'll see if we have some time to come back and explain why it's degree angular scales. Okay, at this point though, this generates a quadrupole pattern in intensity. So the presence of this gravitational wave and the light, if instead of an observer down there, there's an electron on the z-axis, and this light is free streaming through this gravitational wave with some component in this direction, right? Then what that electron is going to see is a quadrupole pattern of light. And so that electron is going to create polarization. And now let's set up so this is a gravitational wave coming straight at us or that electron. Let me draw a somewhat different geometry. And let's imagine, so we're here. This is the last scattering surface, right? This is where that transition happens from opaque to neutral, opaque to free streaming. And we have a gravitational wave propagating in this direction. And now let's imagine we're here and we're looking at the sky in this direction. So if we're thinking about, let's see. So we have this oscillating pattern here of what this gravity wave is doing. So right where I've drawn the lines, that's where we've got say, this pattern where it's expanding space in this direction and compressing it in this direction. And then where there isn't a line, you have the opposite sign. So so it's compressing space in this direction and expanding it in this direction. And that sets up, for the free electrons in here, that sets up this pattern of quadrupole moments. I think this might be too hard to get all this geometry across by my hand waving and drawing, but so we've got, as we're looking from here, so this is view from here. Let's say, in this direction, the electrons, where we're looking, the electrons are seeing this kind of pattern of quadrupole. And then over here, or of gravitational wave. And over here, they're seeing this. What we end up getting from this, because this is, the direction, now we've got the direction of variation is this way. And the polarization that we'll get out of a quadrupole moment like this will be like this, and then this will have the opposite sign. So bring it.
So wouldn't it be the other way around, though? The brighter direction, it's.
Sorry, I think you're right. So now we have a polarization pattern that looks like, if I draw it out and put in the intermediate stuff, looks like this, where this is the direction of variation, and this is a B mode. So the geometry is a little complicated, to follow. The essential thing is that in the scalar perturbation situation, we only have one direction in the problem. It's the direction of variation of the Fourier mode. And with the gravitational waves, we have this additional source that determines the orientation of the quadrupole, and that's the polarization of the gravitational wave. So gravitational waves source both of these patterns. Okay, so now I can tell you the story of how I set back the theoretical discovery of B modes by 2 years. So it was 1994, and my office mate, Arthur Kosowski, who's now a professor at Pitt, was doing his thesis on CMB polarization. And he told me one day, hey, Lloyd, scalar perturbations source Q, but tensor perturbations source both Q and U, tensor gravitational wave. And I said, now I knew this stuff, and I said, well, that doesn't mean anything. These are coordinate system dependent quantities, right? Q and U aren't distinct from each other. You just rotate your coordinate system by 45 degrees, and Q becomes U, and vice versa. And unfortunately, that explanation satisfied both Arthur and me, and we went on to other things. And what Arthur was telling me, without either of us realizing it, there was a definition of the coordinate system implicit in what Arthur was doing, and it came from the direction of variation of the Fourier mode. Arthur was talking about amplitudes of Fourier modes. He wasn't talking about pixels on the sky. And once you bring in that direction of variation, so this is in our coordinate system that's set up by the direction of k. If we always say, okay, we're going to call this x and this y, and define q and u accordingly, setting this in the k direction, then then scalar perturbations only generate Q. They only generate this pattern. That's the important thing. And you cannot change your coordinate system and rotate this pattern into this pattern. These are distinct patterns. So this is a really, why did this happen? What was the failure that Arthur and I had? I mean, there's the obvious one. But as a lesson, I mean, I think that, to this, you go through all this learning of physics, and everything you're learning is written down in textbooks and is known. And now you're at the frontier, and you're not, and you're trying to figure things out, and it's hard to, it's hard to keep in mind that, wait, there's stuff there that no one's discovered yet, right? It's hard to be it's a transition to being in a framework of, we actually might be onto something that no one's ever noticed before. And we weren't enough in that mindset, I don't think. So, yeah.
You said that the gravitational wave produces both E and B mode. So is this drawing here, is that just the B mode, or is that an E combination of
This is a B mode. This is a B mode. You won't get this pattern out of the scalar perturbations. So this is a B mode.
You said that gravitational waves source both E and B modes. I thought this might be some combination of a
Right. No, I got it. Yeah. Sorry. Yeah.
So if I look at the sky now, what is this pattern of H and C that I see in the CMB? Like, what geometry does it have on the sphere? Like the formula behind me?
I mean this pattern?
Yeah.
So if we just saw a single Fourier mode on the sky like that, it would just be this, hot, this band of hot, band of cold, band of hot.
Like circles that get bigger around the equator and then smaller.
Oh, look, I mean, I guess so. Depending on, right now I'm imagining a piece of sky that's small enough we can just treat it as flat, So I'm not thinking about the whole sky.
No, I'm trying to think basically like where is the preferred direction? Because your argument is that there's some like special direction that's K.
Well, K is this direction. K is the direction of variation. Right? And so just like here, this was K. Right? Because the Fourier modes are e to the I k dot x. And if you make your changes in x along K, those are the ones that have the biggest impact on this phase. Right, so that changes things most rapidly. If your changes in x are going in the K direction.
Okay, but at any little patch in the sky where I look, is there a preferred direction like that? The variation is strongest, let's say, from left to right rather than top to bottom.
Oh, we always only in this idealized case where I set up a universe with a single Fourier mode in it, then there is. We have this whole ensemble of modes that we think is a result of some statistically isotropic and homogeneous process. So on an ensemble, there isn't. I mean, of course, there's. So anyway, I hope that clarifies things.
For any given mode, I guess there is a.
That's right.
Yeah.
That's right. Yeah.
Are these two Ks the same K? Because I thought that in the picture on the left with the plasma oscillation, there was like.
I guess.
K was, so that K is like
So.
perpendicular to the other one. Is that?
Yeah, these are really different Ks because, this K I'm talking about a three-dimensional object, and here this is a 2D vector on a piece of sky that's close, it's small enough that I can treat it as a 2D plane. So this is for a 2D Fourier mode on the sky. This is like L, Lx and Ly. So these Ks are a little different. It's in each case they're the direction of variation. In one case it's in this three-dimensional thing, in another case it's two-dimensional. Yeah.
Are the gravitational waves the only source for B modes?
Great question. The question was, are the gravitational waves the only source for B modes? And no. So they're vector. There's in principle vector perturbations. These have no growing mode. So unless you have some nonlinear process actively stirring up new vector modes, you don't get them. The vector modes were important in killing off cosmic string models of structure formation, because they generate vector perturbations, and they create temperature anisotropies and polarization.
What do you mean by vector perturbations? You don't just mean like light, because there are.
No, I don't. Yeah. So if you don't know what that means, never mind. Sorry, but I don't want to get derailed too much. And then, importantly, at second order in perturbation theory, even scalar perturbations can generate B modes. I mean, and the primary process of this is gravitational lensing. And you can imagine that so gravitational lensing has light, light gets deflected. And so if you can imagine this pattern being original E mode, and then different regions of this get deflected in different ways, it will become an admixture of E and B. So gravitational lensing creates B modes out of E modes.
There's going to be any way to distinguish both?
Yes, there is actually, because the gravitational lensing also distorts the pattern of temperature anisotropies and polarization and E mode polarization anisotropies. Well, I guess to keep it simpler, distorting the temperature anisotropies, and we can use that to infer how things have been lensed, and then we can clean the expected lensing contribution out of our B mode maps. So let's see. I'm close enough to go ahead and say something about primordial gravitational waves and B modes. So, but I'm wondering, just let me give the whole story of where these, about primordial gravitational waves and B modes. Just an overview of it. And so you'll recall that in inflation, right, the expansion rate's accelerating, and any given wavelength, say this is one co-moving wavelength here, is going to get stretched till at some point it's bigger than the horizon, c over h. And if we assume that if we just linearize if we assume these metric perturbations are in their ground state, quantum mechanically they can only be so quiet, right? So they're obeying a harmonic oscillator. Any given Fourier mode of metric perturbation is obeying a harmonic oscillator equation. In its ground state, it has a Gaussian distribution for its amplitude. And as that wavelength of the perturbation is expanding, the spread of that Gaussian distribution is becoming shorter. As you might expect, the quantum mechanics is becoming less important as you go to larger scales. But as the perturbation leaves the horizon, it can no longer track it can no longer keep that decrease in amplitude happening. It's frozen in. I mean, causality prevents that from going down. And so we have this fluctuation, this quantum mechanical fluctuation frozen in, and it stops going down in amplitude as the wavelength expands. And I say that to motivate that the amplitude of gravitational waves from inflation is proportional to it's proportional to the expansion rate. The smaller that length, that horizon crossing, the bigger the amplitude of the quantum fluctuations that get frozen in. And then, as they re-enter the horizon, they eventually re-enter the horizon. And their energy dilutes. So Now you below the horizon, this is massless radiation that just like photons, its energy is their numbers are diluting, and then their energy is dissipating due to the expansion. But once photons start free streaming, that generates quadrupole moments, and then polarization. So we get polarization. And so where this, so if you have a gravity wave that is, let's see, maybe I should skip. There was this question about the angular scale, and I said degree angular scales. And that's because the smaller wavelength gravitational waves, they entered the horizon early and had all this time of their amplitudes shrinking before there were free electron, before there was free streaming and they could generate quadrupole moments and create polarization. The biggest amplitude comes from wavelengths that are just crossing the horizon right at decoupling. And the angular scale of the horizon at that time is about a degree. That's why it's degree angular scales. So it's an probe of the expansion rate during inflation, if we could detect this. And I can show you in this plot the current state of things. From John Kovac. And here, so here are the lensing B modes. So we have detected B modes, but they're the ones generated by gravitational lensing. And then out here at degree scales, here are the different theoretical predictions of the contribution to the B modes from primordial gravitational waves. And our upper limits are pushing R to where it's really comparable, pushing the primordial signal to where it's comparable to this gravitational lensing signal. And so we're right at the point where we need to start cleaning out this the lensing signal in order to keep pushing further and hopefully detecting these gravitational waves. All these points in black are from the BICEP-Keck collaboration. We're now working closely with them because our higher resolution data from the South Pole Telescope, we're imaging the same field in order to provide them the information about lensing needed to clean out the B-mode lensing signal. Okay, so any last questions about CMB polarization before we talk a bit about DESI BAO? Yeah.
What is R in that plot? The 0.03 and 0.01?
Yeah, thanks. So this is a measure. So I introduced AS as this amplitude of the scalar perturbations. And it's this ratio of the amplitude of the tensor perturbations to the scalar perturbations. Oh, yeah, I do. Thanks.
This is beyond the scope of the lecture, but can you summarize the sources for bifringens? When do we have circular polarization?
Oh, in order to create, so it's been a while since I thought about this. If you have I think if you have electrons oriented because of a magnetic field, their spins are oriented, then that will change there'll be an index of refraction for the light that's different depending on the polarization and how it aligns with that spin, and that can delay one of these. But anyway, I think I should actually get back to you on Slack rather than talk about that now. Yeah.
Just out of curiosity, the amplitude of the tensor perturbation can be inferred from the CMB, other part of the CMB, or only polarization, only the B mode?
Oh, yeah. So, I mean, so these gravitational waves also create temperature anisotropies. For the same reason I gave you about polarization on degree scales, it's only on degree scales or less. And actually, when I was in Chicago, Mike Turner and I wrote a paper saying that with temperature anisotropy, we're never going to be able to detect R if it's less than 0.1, because it only contributes on large scales. There's only so well you can measure the power spectra out there because you're limited by how many spherical harmonic multipole moments there are. You're trying to estimate a variance from a set of samples from the distribution. There's only so well you can do that. You can't do better than detecting R equals 0.1. You can't push lower than that. And yeah, so at any given L, there's 2L plus 1 M modes, and we're trying to estimate the variance of these ALMs from just a finite set. Okay. So, and I'm right. I chose to wear my CMB S4 T-shirt today, and this is so on the C here is this curl. This is also a curl pattern, not so obvious from what I wrote there, but this is something you'd only get from from B modes, which another anyway. So that's why I have this T-shirt. Okay, switching to BAO. Thank you.
That's the board that doesn't.
Okay, thanks. All right, maybe I'll. Yes. Yeah, there are some experiments for measuring circular polarization. There is some astrophysically measured circular polarization, but as far as like for only upper limits on anything in that could be, this black body spectrum, 2.73 Kelvin. All right, baryon acoustic oscillations. So actually, I wanted to show you a little animation first. So this is basically we're learn a Green's function here of what happens if you have a kind of point over density. How does the plasma and other matter respond later? Actually, let's think of this as tracking the baryons. So we have some point over density, and so pressure is going to drive matter out away from this. And that ring around it will be one sound horizon length away from the center. That's how far that sound wave can travel by the time the plasma disappears. Of course, we've got a whole bunch of overdensities spread out through the universe. And so we get this happening everywhere. And then there are overdensities later when we can start forming galaxies in these patterns. So galaxies form where there's a greater density of matter. So, this is all obviously a toy picture of what's going on here, but just to conceptually get things across, right? So this is, okay, see, galaxies. So now one can make a map of galaxies and study their separations, right? Do a histogram of separations at different lengths. So this is this histogram being created. This should only take about 3 hours to get all these galaxies. Here they're going to speed up. And we expect some excess of pairs on scales of the sound horizon. And that's what we have here. So this feature is this baryon acoustic oscillation peak in this distribution of galaxies. So let's say you do that, and you select some set of galaxies that are all at similar redshifts. So you're taking spectroscopic observations. You can measure the redshift of the galaxy. You can put them in some small redshift bin, and then do this histogram. Or yeah, let's just call it this histogram of pairs. Then, right, we just saw that we get this bump. So this is telling you about the angular size of the sound horizon at whatever redshift this is. That's the angle it projects into. And how is that related to other things? So it's the sound horizon, right? If we're still in the small angle limit. In the DESI papers, they call this dm of z. This is the co-moving angular diameter distance. It's what I called dA of z. RD is defined as it's basically the sound horizon, and the D is for baryon drag. It's the co-moving size of the sound horizon when baryons stopped getting significantly dragged around by the photons interacting with them. So it's a little bit different from the sound horizon I was defining earlier, but basically the same thing. In the interest of time, I'm not going to write all that out. I'm just going to say sound horizon. At last scattering, right? That's and in detail at this end of this baryon drag epoch. And again, this dm of z. This is just what I was calling dA of z. It's this angular diameter distance from us to redshift z. And then there's another signature. We can also pick a set of galaxies all at the same redshift and count pairs all at similar redshifts, but with different redshifts, all on the same line of sight. So in the very close to each other along the line of sight of the sky, and we can do a histogram of, well, how far in redshift are they separated? So this, I should write this as delta z. And I guess that can go both directions, but let's just look at the, and we'd also get a peak. Right? This is the same feature in the distribution of galaxies, but now it's just along the line of sight. So we got more pairs. So this is, we might call this delta z sub s. It's also a function of z. This is this feature projected into redshift space along the line of sight. And we get this, we have this relationship. Right? This looks like this is some local version of Hubble's law. So this is if we know RD, say from modeling the microwave background data with, say with LambdaCDM, we know RD, and we can measure this delta zs and infer h of z. So these are the fundamental observables for baryon acoustic oscillations, and DESI is measuring these things. They define some things like so instead of plotting h of z, they plot this, And then they also define this quantity, which is this combination I'm telling you about these because I'm going to show you them in plots. And then in my notes, which I'll post, there's derivations of these expressions I'm about to put up. But in the interest of time, I'm just going to put up the expressions relating these things to observable to theoretical quantities. Delta z sub s of z equals rd h of z, and so this equals rd h naught. So this is assuming lambda CDM. So this is right. This is the contribution from a cosmological constant, which is in lambda CDM is omega lambda is just 1 minus omega matter. Here's the contribution from matter density. In general, this is the whole. This would be depend on all the. Well, this would the dark energy part could vary with time. There would be contributions from neutrino masses, but these are the dominant contributions that we get in lambda CDM. And then for theta s of z, right, this is r d over dm of z. This works out to rd h naught over this integral from 0 to z of dz prime over the square root of omega matter times 1 plus z cubed plus 1 minus omega matter. This is h of z over h naught, and it generalizes just like this. I just described this. This is h of z over h naught. So this is h of z over h naught down here, and the same thing I said about this applies here in terms of more general model spaces. But in lambda CDM, there's only two things that the BAO measures. These BAO they measure RDH naught, the product. There's nothing that breaks this degeneracy between what's RD and what's H naught, and at least in just the BAO data, and they measure omega matter. So those are the two things. In lambda CDM, what we get out of this, I won't write down the actual values, but they're more generally, they're sensitive to RD times H of Z. Yeah.
I noticed the square roots don't have any terms for omega radiation.
Right, and that's because this is at very low redshift. So they're only measuring this up to redshifts of 2. So the radiation density is very small. In principle, it's there, but that's why I neglected it.
Potentials would decay anyway, right? If you have a lot of radiation, then this wouldn't survive.
That's right. So all of the structure that we're seeing in these, the galaxies themselves might not exist, right? If we had all this radiation around, yeah. That's right. Yeah.
So it's
And-
not important on part.
And again, again, more generally, this is H of Z over H naught. And there will be some small contribution to this we expect some small contribution to this from neutrino masses. That's the most important thing I've neglected in this expression. We're not really sensitive to it yet at this level of precision. But it makes a difference. I expect we'll get there, or that's important to include. in terms of understanding the data. And okay, so here are the measurements. So remember, this dV is this product of the dA, where you're measuring right transverse to the line of sight. You're getting the angular separation, and then the dH, where you're going along the line of sight and you're learning this, right? dV is this combination of the two. They can measure this more accurately than any of these things individually, and so they chose to plot this divided by RD, because that's what they're sensitive to, the ratio to the sound horizon. And then for plotting purposes, it was convenient to put in this z to the 2/3. And these are the measurements from different kinds of sources that they're using, that they're getting redshifts of. So Lyman alpha forest, quasars, emission line galaxies, luminous red galaxies, a bunch of different things over this range of redshifts out to 2 point something. And what's in gray are the predictions of the LambdaCDM model given the Planck data. And and this is how those residuals look. And then this is this ratio between dm and dh. Another thing they plot here, and anyway, here's again the predictions of LambdaCDM, and then where their data lie, it's actually, so anyway, so this is all interpreted within the LambdaCDM model. There are some discrepancies. If we look at the biggest discrepancy here, well, there's this point here, and that's important for their this point this point plays some of their, anyway, what they claim, they also look at dark energy models where the equation of state is varying as a function of time, this equation of state parameter. So the dark energy density is varying, and they claim that there's a 2 point something sigma better fit for that. And then if you combine with supernovae data, depending on what supernova data set you use, those are also measuring a distance redshift relation. And depending on what you combine with, the preference of a time-varying dark energy over LambdaCDM is at up to the 3.9 sigma level. Yeah.
I'm seeing that the points that are off are these LRG points. So what is LRG?
LRG is luminous red galaxy. So it's a particular kind of galaxy.
Like
These
the
are
one that are off in both, the orange and the red, with respect to the others.
that's true. And these points are really important. Both of these points are important for driving that difference, that preference for time evolving. And then, a cautionary point about this one is that this is 3 sigma different from a previous measurement of comparable signal to noise. So I think that this is early days. This is a significant jump forward in precision. This is their first year of data. I'm really excited to know what's coming out. They already have 3 full years of the survey done, and they're also going to be coming out with not just these geometric measurements, but also measurements of the amplitude of structure that will weigh in on this question as well. So I think this is really exciting. I'm my take on this was, well, this is probably a fluctuation away from LambdaCDM. We don't know yet. I was actually interested in it enough. We were, there's another thing I can show you. If I can actually control, all right, I gotta come over here, collapse that, and then, actually just submitted a paper to the archive this morning. Well, I didn't, my student did, but I've been helping him with it all week. And Here's another, here we're plotting up their data. So this is another look at it. And here we can see these best fit W0, WA, CDM curves. So that's letting these two parameters controlling the equation of state of the dark energy variable W0 and WA. And you can see how, right, this point here at z equals about I guess it's a 0.5, right, is pulling them down here. And then there's also this point at z equals 0.7, right? So these are those 2 points that are most discrepant from LambdaCDM. And this blue line is, coming down here to try to grab that, and also coming down to try to grab that. We took a different tack on this. We've been wondering if we had just written a paper when this came out trying to reconstruct the recombination history. So that as I've emphasized, the temperature is sensitive to how the universe recombines. The polarization is very sensitive to that. And we can use that data to actually just reconstruct how the universe recombines. And if you free that up, it has implications for the DESI data. And so we're assuming LambdaCDM, but letting recombination just be free, because maybe there's some physics affecting how recombination proceeds. This is the constraints from Planck and LambdaCDM on omega matter and H naught. If we assume LambdaCDM constraints from Planck, if we free up recombination, then the Planck data just constrain us to be in this plane. And the DESI measurement of omega matter, right? I told you there's 2 things they measure, RD times H naught and omega matter.